Hi, welcome back. In this lecture I will present a formulation of the finite element method in a 1D configuration. The problem that we want to solve is the following presented in this slide. As the first model problem, we choose a second order of the ordinary differential equation, namely the 1D Helmholtz equation. We already seen the Helmholtz equation in the finite difference module. As you can see, there is a second order differential equation. The unknowns that we try to determine is called f. Here we have the second order differential equation and then plus a term including our unknown f, and then equal to s, that is another function that is the source of the problem. Our domain is defined between a and b, and then we have two boundary conditions at the extreme of our one-dimensional domain. So the Helmholtz equation is an equation that describes many physical systems. One important example for SEM is the propagation of a transversal wave in a 1D medium in a dielectric. Such a light wave propagating has also been reflected in dielectric layers. So in particular, these alpha and beta are going to be our material coefficient when we solve the Helmholtz equation for 1D propagation problem. So what are the steps that we need to do for solving the Helmholtz equation using the FEM method? Well, we saw that the first step is to discretize the equation. So we divide our interval, in this case going from -2 to 5, we divide in 7 cells. So the first step is discretizing. So we do the discretization in 7 intervals that are, in our case, are called elements. So in our case, A is equal to 2 and B equal to 5. So here there is a typo, should be actually A equal to -2. And then we divide the domain in 7 intervals. So 1, 2, 3, 4, 5, 6, and 7 intervals. We call the endpoints of each element nodes. So if in the case of 7 elements, we will have 8 nodes. So we will have a node here, 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 and here. So the number of nodes is equal to the number of elements plus 1. So each of these nodes will have a coordinate xi, I -3, where I is going from 1 to 8, so for each of the node. Probably the most important aspect of FEM is the introduction of the so-called basis nodal function. So these are functions that are linear in the interval of the nodes and the nodes -1 and then the nodes +1. So let's take the example of node 1, 2, 3, and 4 in this case. So we're going to have these functions that are linear for in the domain from node, in this case 4 to 3, and then node 5. So from 4 to 5 they're going to be linear in the shape. I cite this domain that includes this element here and the element here. The function will be 0. So the nodal basis function are linear function on each interval in the adjacent domain. Is 1 at node I, so in this case you see that is 1, and 0 at all other nodes. So these basis functions are often called tent function. So in the plot you see here in the right, you see 1D linear elements. The basic function phi 4 is emphasized by the thick line, so here. If we take f3, that is the basis function with index 3, then our basic function will be the following. So it's here, then we have a linear behavior between -1 and 0 is going to be 1 for the nodes equal to 3, and then is going to have a linear behavior from 3 to 4 node. The rest will be all 0, aside here and here. So the second major step is to use actually the nodal basis function. So we seek approximate solutions that are expanded in the basis function. In the following, f will denote this approximate solution. So f is equal to the series from 1 to 8 of a basis function that we define as a 10th function multiplied by amplitude. And our problem will be determine this fj by using this weak form formulation, but we see in the next slide. So our job will be then to determine this fj. So note that f, I define that xi is equal to the fi. So the expansion coefficient are nothing else than values of f at the nodes. What happens at the boundaries? Well, since f defined in A is equal to fa and f defined in B is equal to fb by definition of the boundary condition, we set f1 and f equal to fa and we define f8 equal to fb. So these are defined by the boundary condition. So the next step, we follow the Galerkin method, that is nothing else than to choose the test function equal to the nodal basis function. So in this case, wi is going to be equal to f the phi I, where I are going from 2 to 7. So we don't use the two nodes that define at the extreme of the boundary, since those are already defined by boundary condition. So the boundary points are excluded because the corresponding function values are known. The second step is to define the residual. So in this case, the residual will be nothing else than our Hellman's equation. We move to the left side the s function that is our source. So we take this residual function and then we multiply by the test function wi. And then we want to complete an inner product. So we take the integral from a to b over dx, and we set this to 0. So we want this inner product or integral equal to 0. So when we take the integral of this residual multiplied by the test function equal to 0, this is going to be our equation that we want to solve. And this is what is called the weak form equality. And then we work out the integral itself. So in particular, we're going to use integration by parts. So to move one derivative from f to the text function wi, we use integration by parts. So this gives the weak form of the original form, which is the weighted average of the residual. So this is the results of our integration by parts. Note here that one of the derivative moved to our test function wi as a result of applying the integral by parts. Also note that when we calculate this, the original integral of the residual multiplied by the test function, one of the term coming from the integration part, that is the calculation of this term here, wi alpha f prime, vanishes in at b and a, since our text function are going to be 0 both in a and in b. So we now want to get the equations that we want to solve by solving a linear system. So what we are doing is picking up w2 equal to f2. So we just get the first equation. So the first step, we are going to substitute this function here in this equation here, and then we are going to use one specific weight function, so one that is also one specific nodal function, that is 5 of 2. So we are going to do this step here, and then we are going to get w2. That is also f2. So we're going to substitute in this equation here. Because of this expression here, we substitute here, we generate an equation involving 6 unknowns. The coefficient fj for the interior nodes x of j, where j are the index in the inner part of our domain. So we do this replacement, and then we put f2, and then we will have an expression with the sixth term. So, and this will constitute one of the equations that we want to solve. However, we have 6 unknowns, so we will need 6 equations. So what we're going to do next is we do exactly the same procedure, but we're going to use a W3 that is equal to the nodal basis function in Galerkin method. So we can choose a different weighting function. So we do weighting function 2, 3, 4, 5, 6, and 7, and we're going to get 6 equations with the 6 unknowns. So in the end, we have 6 equations and 6 unknowns that are our Fi, and this can be formulated as a system of a linear equation. For instance, a z equal to b, where z is our unknown fj, and aij are the terms coming from our integral. So you see, our integral from the previous slide becomes this integral on this slide. And each element of our matrix will be defined by the calculation of this integral in this slide here. So you see here we have alpha that is multiplying of I prime phi prime of j, and then we have term that is just taking the values of the function phi y and phi j multiplied by b. And then our b, that is the source term we have in this linear system, will be also an integral, and will be an integral from a to b of the source function multiplied by the test function. In this case, there are also the nodal function, since we are using Galerkin method. So note, in our problem, A has 8 columns and 6 rows, Z has 8 rows, and B has 6 rows. The coefficient f1 and f8 are known from the boundary condition and can be moved to the right side. So this is the slides that represent the final system using the definition I showed in the previous slide. So you see we have a matrix here, that is our matrix A, that is also called a stiffness matrix. And then we are having the terms of our known, in this case are Z or F, equal to the source term multiplied by some terms coming also from minus a vector that is coming from the boundary condition. So the part of the system matrix A that remains on the left side is squared. And we have, that means that we have as many unknowns as equation. The matrix A is called stiffness matrix and is a sparse, as the basis function, our tent function, give only nearest neighbor coupling of the unknowns. Note also that A is a symmetric, so this term is equal to this one, and this one to this one. So Aij is equal to Aj. So this is related to the fact that Helmholtz operator, as we saw in the module of finite difference, is a self-adjoint operator. And also we use Galerkin method, so our test functions are equal to the basis function. So this was the last slide of this lecture. In this lecture, we are going to see how this extrapolate to the problem. Talk to you soon.